We spent the last few weeks studying electricity and then magnetism. Today what we're going to do is combine the two into a phenomenon that we call electromagnetic radiation. Let me tell you about where electromagnetic radiation comes from, how it was discovered, when the theory came about first. I look back to 1861, 150-ish years ago, 160 years ago almost. James Clerk Maxwell, a Scottish guy. You don't see a lot of Scottish physicists, but this is one of them. Okay, in 1861, James Clerk Maxwell said that accelerating charged particles, you know what that means, right? Charged particles like electrons, protons, alpha particles, whatever, anything that's charged and is accelerating, not just moving, but accelerating, generate changing magnetic fields. So if you have a charged particle that's at rest, it will generate an electric field. It'll also generate a gravitational field. If it's moving at a constant speed, it'll generate an electric field, a gravitational field, and a magnetic field. If it's accelerating, then it will generate not just an electric field and a gravitational field and a magnetic field, but specifically it'll generate a changing magnetic field. And that's going to become really important later on, the fact that it's a changing magnetic field. Not just any magnetic field like moving charges generate, but a changing magnetic field. So accelerating charges generate changing magnetic fields. Similarly, changing magnetic fields will generate changing electric fields. That's why this concept of changing is so important. We need magnetic fields to generate electric fields. And magnetic fields won't generate electric fields if they're just constant magnetic fields. You need a changing magnetic field to generate a changing electric field. Hence, in order to get this electric field, then you need this accelerating charge. So, accelerating charges generate changing magnetic fields. I'll call it delta B, for lack of a better term, changing magnetic fields, which generate changing electric fields. Which, well, changing electric fields generate changing magnetic fields. And then changing magnetic fields generate changing electric fields, and then changing electric fields generate changing magnetic fields, and so on. So what you end up getting from an accelerating charged particle is this wave of changing electric and changing magnetic fields. You get electromagnetic radiation. That's what causes this whole thing, right? We watched the video a few minutes ago. We saw all these different types of EMR and some of the different things that they do, some of the different things they're responsible for. Ultimately, it always comes from accelerating charged particles. Okay, in order to get EMR, which consists of changing electric and changing magnetic field waves, you need to have an accelerating charged particle. Because if you just have a moving charged particle, it'll generate a constant magnetic field. And it'll generate a constant electric field. But the magnetic field won't produce an electric field, and the electric field won't produce a magnetic field, therefore we can't get the EMR. It has to be accelerating to generate the changing magnetic field, to generate the changing electric, to generate the changing magnetic field, and so on, and so on, and so on. Electromagnetic radiation is energy. That's like fundamentally, that's what it is. Energy that travels in a wave-like form, travels as a sinusoidal wave. Do you guys remember from Physics 20, transverse versus longitudinal waves? The transverse waves were the waves that looked like the water waves, and then the longitudinal waves were those waves with compressions and rarefactions. Or like when you push a slinky like this, back and forth like this, as opposed to waving it like this. Electromagnetic radiation is energy that transfers in a wave-like form, a sinusoidal transverse wave. But the difference between this kind of wave and what you did in Physics 20 is that an electromagnetic wave doesn't need a medium. It doesn't need a material to go through. Okay, all the waves that we did in Physics 20 required water or air or whatever to travel through. EMR is just pure energy that travels in a wave through, well, can travel through just about anything, including nothingness, including empty space. It consists of changing electric and magnetic fields. Here's that big word again. Remember I told you in the last unit, you're going to see this a lot in magnetism and in EMR. Changing electric and magnetic fields perpendicular to each other. So if the electric field wave is this way, the magnetic field wave is this way, perpendicular to it. Perpendicular to each other and in phase with each other. That means that when you have a crest of an electric field, you also have a crest of a magnetic field. And when you have a trough of an electric field, you also have a trough of a magnetic field. In phase with each other. And this is the big thing right here, right? To summarize it all, it's caused by these accelerating charges. Why is it caused by accelerating charges? Well, because it consists of changing electric and magnetic fields. And the only way to get changing electric and magnetic fields is to have an accelerating charge. Not just a moving charge, but an accelerating charge. So remember, stationary charges generate gravitational and electric. Moving charges generate gravitational, electric, and magnetic. Accelerating charges generate gravitational, changing electric, and changing magnetic, which give us electromagnetic radiation. Here's what it looks like. By the way, it travels perpendicular to both of the waves. Here's what it looks like, and this is kind of a tough diagram to draw, but do your best. We've got three axes here, X, Y, and Z. We've got the electric field on our y-axis here, the magnetic field on our z-axis, and the direction of propagation or the direction of movement on our x-axis. Now, understand that it doesn't matter which of these three axes each of these different variables are on, as long as they're all perpendicular. Again, that word, perpendicular. Okay, I've got electric on the y-axis, magnetic on the z-axis, could just as easily be reversed. They're traveling along the x-axis, does matter, could travel along the y-axis, as long as the electric and magnetic fields are on the x and z-axis. So as long as we have all three axes with each variable on a different axis, it doesn't really matter which axis is which. I want you to just stop drawing for a sec, stop writing and stop drawing for a second, and just look up here, okay? I want to try to demonstrate what this looks like in 3 dimensions. Maybe it looks a little bit better, maybe a little bit easier to see than what we have up on the board here right now, okay? So over here, on this side of the room, we have this accelerating charge. Whatever's causing it, okay, whatever's causing this acceleration charge, whatever, it's there, it's accelerating. Let's say it's going back and forth. As it goes back and forth, it speeds up, slows down, stops, changes direction, speeds up, slows down, stops, changes direction, speeds up, slows down, stops, and so on. So it's accelerating back and forth, back and forth, back and forth for whatever reason. Okay? That will generate this, a changing magnetic field. Actually, let's be consistent with the way that I have it there. Let's say a changing electric field. Got that? Generates a changing electric field. And it generates a changing magnetic field. Notice that it's perpendicular. Do you see that? We have a crest of an electric field, and we have a crest of a magnetic field that's perpendicular to that. Okay? So now watch this. Okay, my left hand is going to represent the electric field. My right hand is going to represent the magnetic field. And try to follow along. Okay? And before you make fun of me on this, okay, this is way harder than it looks. Okay? This is way harder to do than it looks. And if you don't believe me, try it yourself. Okay? Electric field, magnetic field. Okay? So they go together, the electric field and the magnetic field. So now the electric field, right, this electric field will now produce a magnetic field like this. And this magnetic field will produce an electric field like this. So what you get is, okay, see what I'm doing there? See that? Can you understand that? And then this magnetic field, sorry, this electric field will produce this magnetic field. And this magnetic field will produce this electric field, and so on and so on and so on. So it ends up going like this. Accelerating charged particle produces this, which produces this, which produces this, which produces this, and so on. So that you end up getting this continuous wave that looks like this. See what I'm trying to do here? Okay? It's hard. It's just like trying to do this and all at the same time, right? Do you see what I'm trying to do there, though? Now, how do you get, like, if I have an accelerating charge that just accelerates and it's done, okay, then I get this, which causes this, but that first little wave that I had, let's say this causes that. This is gone now because the energy has transferred into the new crest and trough. Does that make sense? But if I have the charged particle continuing to accelerate back and forth, then this causes that. Now there's a new this in there to take its place because the charged particle is still accelerating. Does that make sense? So the energy from this goes to the energy for that. And if the charged particle is no longer accelerating, this is gone. And now we have that. But if the charged particle continues to accelerate, then this turns into that, but this gets replaced by more energy, and it just keeps going. So it ends up looking kind of like this, right? You can see, or kind of like that. You can see that we have an electric field represented by this heavier line here. The magnetic field, which you can see is perpendicular to it, in phase. Crest goes with crest, trough goes with trough, and traveling perpendicular to both of those waves. So we'll say electric field number 1. We'll call this electric field number 2. We'll call this one magnetic field number 1. We'll call this one magnetic field number 2. We'll say electric field number 1 causes magnetic field number 2, which, well, now we're out of space on our diagram here, but magnetic field number 2 would cause, what do you think it would cause? It would cause an electric field number 3. We would say magnetic field number 1 would cause an electric field number 2. Right, this magnetic field number 1 causes electric field number 2, and then electric field number 2 would cause magnetic field number 3. Does that kind of make a little bit of sense? Really, I maybe should have put the delta in front of it, because electric field doesn't cause magnetic field doesn't cause electric field. Changing magnetic field causes changing electric field, and so on, right? So see that it's changing here, that the sinusoidal nature of this indicates that it's changing, right? Now we're going to talk about electromagnetic radiation in 2 respects in this unit, one as a wave and one as a particle. We're going to focus on the wave nature of it for the next couple of weeks, and then we'll look at the particle nature of electromagnetic radiation. For now, let's look at some of the properties that support the wave nature of EMR. You guys remember from Physics 20 what diffraction is? We're going to deal with diffraction in quite a bit more detail later on in the unit, but let me just refresh your memory right now what it is. Diffraction is the spreading out of a wave. So if this is a wave that's going towards an opening like this, that wave goes through the opening like this, but as it goes through the opening, it spreads out like this. Does that ring a bell? The spreading out of a wave. It's not the bending, it's not changing direction, it's just spreading out as it goes through an opening or around a barrier. That's diffraction. And you know what? That's a property of waves. That is clearly a property of waves, and I should say it's exhibited by EMR. We observe this in EMR, therefore EMR must be a wave. Right? If a wave property is exhibited by EMR, then logically EMR must be a wave. Interference, maybe remember this from Physics 20, if you have 2 waves, let's say wave number 1 and wave number 2, encountering each other like this, then it produces an interference pattern, either constructive or destructive interference. In this case, it would be constructive interference. You would see something like this. Right? The constructive interference of those two waves. Well, that's a property of waves, but it's exhibited by EMR. In other words, if you take light and you have more light and you put them together, then you get brighter light, right? One flashlight, two flashlights, put them together, you get constructive interference, right? Brighter light, higher amplitude light. Interference is a property of waves that's exhibited by EMR, therefore EMR must be a wave. Refraction is the bending of a wave. When a wave goes from one medium to another, it changes direction. So let's say there's a boundary between two media, medium 1 and medium 2, and the wave is going like this. And then when it encounters the boundary, the wave changes direction. Instead of going like this, now it's going like this. Refraction. We'll talk about that in quite a bit more detail this unit as well, later on in the unit. That's a property of waves, but it's exhibited by EMR, so therefore EMR must be a wave. Now, all these things that are wave properties that EMR does, the only logical conclusion is the EMR is a wave. Which, when we look at Maxwell's theory, right? Maxwell's theory, accelerating charges generate changing electric, generate changing magnetic, and so on fields. Well, then, like it goes with that, right? It flows nicely with that, with his model of electromagnetic radiation. Polarization is the only one of these wave properties that we didn't talk about in Physics 20. So I'm going to briefly explain to you what that means. We won't go into any kind of detail on that at all, but we'll just tell you what it is so that you understand what it means. Polarization is the filtering of a wave. Filtering of certain components of a wave. Like let's say you have a piece of plywood. And that piece of plywood has a little opening cut into it like this, a vertical slit cut into the piece of plywood. And you have a rope that goes through that slit, through that opening. So here's the piece of plywood right here. Okay, McKenna's got one end of the piece of rope, and I've got the other end of the rope. Okay, if I flick that rope like this, then it produces a sine wave like this, right? How much of that wave goes through? How much of that wave goes through this vertical opening? Okay, if I flick it like so that the wave goes like this, then the whole thing is going to go through that vertical opening, right? But if I flick it like this, and the wave ends up going like this, how much of this horizontal wave goes through that vertical opening? None. We would say that that wave was polarized vertically. So only the vertical component would make it through. If I went like this and did it diagonally, how much of it would go through? The y component would go through, right? It would be polarized vertically. We'd get part of the wave going through in that case, but not all of it. If I did this, all of it would go through. If I did this, some of it would go through. If I did this, none of it would go through. It's polarized vertically. We've filtered out all the components but the vertical component. Okay, we're allowing only the vertical to go through. Now, similarly, if I had a piece of plywood with a rope and I cut a slit in the piece of plywood horizontally and I flicked the rope vertically, how much of it would go through? None. Horizontally, all of it would go through. If I did it on some kind of angle like this, then the x component or the horizontal component would go through. We would say in that case that it was polarized horizontally, right? Okay, what if now imagine this. If I took these two pieces of plywood and I put one in front of another. So I've got the one that's vertically polarized right here, and then I take the one that's horizontally polarized and put it right here. And I put the rope through. Once again, I put the rope through the middle. and I start flicking it vertically like this, how much of that vertical component makes it through? None, because it's filtered out by the horizontally polarized piece of plywood, right? How much of the horizontal component makes it through? None, because it's polarized by the vertical polarized filter, or the vertical polarized piece of plywood, right? If I do it like this at an angle, how much of it makes it through? None. The X component gets filtered out by the Y piece of plywood, the vertical plywood, and the horizontal component gets filtered out by the, what did I say? The horizontal gets filtered out by the vertically polarized plywood, and the vertical gets filtered out by the horizontally polarized plywood. So what makes it through? None, right? That's what polarization is. Polarization is a property of waves, but it's exhibited by EMR. So 4 properties of waves that are all exhibited by EMR, which lends credence to Maxwell's idea that EMR is a wave that consists of electric fields perpendicular to magnetic fields, perpendicular to the direction of traveling or the direction of propagation. All right, now I want to distinguish between the types of EMR and recognize some of the properties of the different types of EMR. And this is where this handout that I gave to you at the beginning of class is going to come in. This is also where the video that I showed you at the beginning of class is going to come in. We're going to first write down the 7 types of EMR in order in terms of increasing frequency. So from low frequency to high frequency, which, by the way, low frequency would correspond to low energy, and high frequency would correspond to high energy. So if we rank them in terms of frequency, we're also ranking them in terms of energy. But conversely, increasing frequency would correspond to decreasing wavelength. If you have a low frequency, then that means you have a high wavelength. And if you have a high frequency, then that would mean you would have a low wavelength. So you will be asked to rank these. You will be asked to rank some or all of these down the road. It's a certainty. You may be asked to rank them in terms of increasing frequency or decreasing frequency, or increasing energy or decreasing energy, or increasing wavelength or decreasing wavelength. I want you, every single time you get a question like that, regardless of how it's asked, to remember them in the order of the song that you heard at the beginning of your class, and that's increasing frequency. Write them down that way, and if you have to recite them opposite to that, then just read it backwards. Read your list backwards. Does that make sense? All right, what's the first type of EMR, the lowest frequency of EMR? Radio waves. Radio waves, which sometimes they can break down radio waves into subcategories. What's one subcategory of radio waves that we might have? AM. Yeah, AM would be kind of on the lower end. What's another kind of radio waves? FM. You know that TV uses higher frequency, but still within radio waves. Television. Okay. Radar uses radio waves. You see those when you're near the airport. You see that big ball, that white ball. Okay, that's the ground radar. Okay, that one that's really, really low at the airport is the ground radar. It tells the air traffic controllers where all the planes are on the ground. And there's another one nearby somewhere that's higher up, which is the air radar, right? The airspace radar. What comes after radio waves? Microwaves. I'm sorry? That's radar is next. Honestly, you don't usually have to distinguish between types of radio waves. Okay, if you remember that radio comes first, you're usually okay there. And even if you did have to distinguish, you're usually given some kind of extra clue as to what order they would go in. Microwaves comes next. Hey, where do you think cell phone waves, like the EMR that cell phones use to communicate, would fall? actually fall in microwaves, the lower end of microwaves. Yeah, so when you put that cell phone up to your ear, or remember this one. Okay, when you're trying to sneak the Snapchat in class, and you're sitting at your desk, and you've got your phone down here. Okay, Snapchatting all class. Okay, remember it's microwaves that you're zapping yourself with. Okay? So just remember that the next time you want to put your phone underneath your desk and Snapchat somebody, text somebody. You know what, the power, it's the same microwaves that you use in a microwave oven, but the power is so much lower that there's conflicting opinions on this, but generally it's accepted that cell phone signals are not harmful. They're not harmful to us, although the jury is not quite 100% decided on that yet. What comes next after microwaves? Infrared. Yeah, infrared. Which, infrared, hey, where does infrared manifest itself in our daily lives? Heat. Yeah, it's heat, thermal energy.
How do you spell infrared?
Infra. You're all... We spell it infrared. Infra. Infra means under, below. So infrared would mean under red, below red. What's the next type? Visible light. And visible light is made up of, you guys learned this in grade 1 or grade 2, it's made up of Roy G. Biv. Red, orange, yellow, green, blue, indigo, and violet. It's infrared, below red. And what comes next? UV, which is ultraviolet. What does ultra mean? Over, above violet. Okay? Above the last type of visible light. Ultraviolet. There's different ranges of UV as well. UVA, UVB, UVC. I get mixed up as to which one is which. But you look at sunscreen and it'll talk about protecting against certain types of UV light. Sunglasses, same thing, protects against this type and this type. And again, I always get mixed up which is which. But
how come they say that microwaves are more dangerous than visible light if it's left lower frequency?
Well, I wouldn't suggest that microwaves are necessarily more dangerous than visible light in certain contexts. But the way that microwaves work, like how does a microwave cook your food? Well, sorry? Yeah. Water molecules in food have a resonant frequency or natural frequency at which they want to vibrate, okay, which corresponds to about 2.4 gigahertz, which is in that microwave range. So when water molecules in your food are exposed to these microwaves, then they start spontaneously vibrating, which generates heat, generates thermal energy, and it cooks your food. Right? Does that make sense? There's nothing inherently dangerous about that, right? But the effect that can potentially have on people, I mean, it could be serious, right? There's nothing inherently dangerous about causing water to boil, but depending upon context, it could cause, yeah, if it causes your blood to boil, for instance, yes. Yes, good example, Jack, yes. Then that probably wouldn't be good, right? Does that kind of make sense? Yeah. What comes next? X-rays. And the last one that we have are gamma. Now, we have visible light, which is Roy G. Biv. Those are colors or different ranges of frequencies of invisible light, right? Radio waves, AM, FM, radar, and so on. Those are like different colors of radio. UVA, UVB, UVC, different colors except that we can't see them, right? But different frequency ranges of UV. They all have different ranges, right? It's not like that X-rays have one particular frequency. They all have ranges of frequencies. It's just that these are the more common subcategories that we see. All right, now, how are each of these produced? How are each of these produced? Well, the reason that we've color-coded them in the way that we have is because it helps us to see the similarities between how they're each produced. They're all produced in general by accelerating charges, but specifically, we would say the first two, radio waves and microwaves, are produced by what we call oscillating electric charge. Oscillating electric charges. That means the electric charges that are going back and forth, back and forth, back and forth. Even the electric current in our houses generates radio waves. Because that electric current, those electrons are going back and forth at 60 cycles per second. Back and forth, back and forth, back and forth. It would just be extremely low frequency radio waves of frequency 60 hertz, and low power radio waves as well. It would not be harmful. Although, I know my in-laws live in Sherwood Park, and a few years ago, there was this massive controversy in Sherwood Park just on the other side of the houses across the street from them, because there's this utilities corridor, this massive utilities corridor. If you know Edmonton, Sherwood Park at all, there's these oil refineries up on one side, and they built this massive power line on the other side of the highway. My in-laws live just in that neighborhood that's by those power lines. And I remember before they built these, like everybody in that neighborhood was against these power lines coming up because they felt that they were dangerous because of the essential. Well, most people that speak against it don't really know why they're necessarily speaking against it, like what the potential harm is. But ultimately, the concern would be the generation of radio waves. There's no real evidence to suggest that it's dangerous, but that's the fear that people have, is these radio waves produced by these oscillating electric charges would cause harm. Okay, infrared, visible light, and ultraviolet. They're all produced by transitions of electrons in atoms. So when an electron is on the third level and it falls down to the second level, it produces EMR. Or when it falls to the first level, it produces EMR. Different transitions result in different frequencies of EMR, right? So it's not like it's all produced by the same transition. Different transitions in different atoms result in different colors or different frequencies of EMR. Now, X-rays can be produced this way as well, but it would have to be like a massive transition. So we don't put X-rays in the same category as infrared, visible light, and ultraviolet. X-rays are generally produced by, what I should have done is had two different colors here for X-rays and gamma rays, because they're produced in different ways. X-rays are generally produced by rapidly decelerating electrons. So electrons that are going really, really, really fast, you smash them into a target, and they stop almost instantly. The kinetic energy of those electrons has to go somewhere. Well, it goes off into producing an X-ray photon. So if you go to the dentist office and they do an X-ray on you, that's what happens, right? They have this X-ray tube, which causes the electrons to go to incredibly high speeds, like 10 to the 4, 10 to the 5 meters per second, and then they get smashed into this target, generating X-rays. And then those X-rays, with a high penetrating power, go through your skin and see like the holes in your teeth and so on. Gamma rays are produced by nuclear decay. Another way to say that would be radioactive decay. In the end, nuclear decay results from having matter converted to energy. And we'll spend quite a bit more time in our last unit near the end of the course talking about how that happens, details of that. Now, the last thing I want to do with you today, tell you about some good news and some bad news with regards to these boxes that are not filled in here. Do you want the good news first or the bad news first?
Bad news.
Bad news first? Okay. Here's the bad news. There are 7 different categories of electromagnetic radiation. If you are given a frequency of EMR or a wavelength of EMR or an energy of EMR, you have to identify what it is. So in other words, that's 21 different ranges of frequency / wavelength / energy that you have to be familiar with. That is bad news. The good news is, because I am terrible at memorizing things like that myself, I look for ways to kind of cheat. And I found one.
Nice.
A way of cheating without really cheating. Here's what I want you to do. I want you to, let's talk about frequency first. I want you to not memorize 7 frequency ranges. I want you to memorize 3 frequency ranges. I want you to memorize that microwaves fall in the range of 10 to the 9 to 10 to the 12 hertz. X-rays fall in the range of 10 to the 17 to 10 to the 20 hertz. And visible light falls in the range of 4 times 10 to the 14 to 7.5 times 10 to the 14 hertz. So that's see that that's a much smaller range, right? Visible light is a much smaller range. And that's why we're being so precise there in including the base, because it's such a small range. Now, why do I only want you to memorize those 3? Well, what if I give you a frequency that's 10 to the 11 hertz? What kind of EMR is it? Microwaves, right? What if I give you one that's 10 to the 7? What is it? Radio waves. You didn't need to memorize the range of radio waves, right? If it's below microwaves, it's got to be radio waves. What if I give you 6 times 10 to the 14 hertz? What is it? Visible light. What if I give you 9 times 10 to the 14 hertz? What is it?
Ultraviolet.
Ultraviolet. What if I give you 10 to the 21? What is it?
Gamma.
What if I give you 10 to the 18? What is it?
X-rays.
The 18 is X-rays. What if I give you 10 to the 15?
Ultraviolet.
Ultraviolet. So memorize those 3 ranges and then fill in the blanks for all the other frequencies that you could have, right? Okay, so now we said 21 different ranges. 7 of them are taken care of by memorizing 3 ranges, right? The news gets even better here. If you're given a wavelength, then what I want you to do is use this equation that you learned in Physics 20, rearrange it to solve for frequency, say V, the speed of light, is 3 times 10 to the 8 meters per second, divide it by the wavelength you're given, and get what? Get a frequency. And then compare it against the 3 frequency ranges that you just memorized. So now we've taken care of 14 different ranges by memorizing 3. It just means a little bit of work, right? If you're given a wavelength, you've got to calculate frequency from the wavelength and then compare it against the 3 frequency ranges that you've memorized. Yep?
So the middle one was 4 times 10 to the 14, 7.5 times 10 to the 14?
Yes. Now, that takes care of frequency. It takes care of wavelength. Energy, I'll tell you, we're going to deal with that in a similar way. There is an equation that relates energy to frequency. I'm not going to give it to you right now. That's going to come later on in the unit. But just know that if you're given an energy, you will, in the next couple of weeks, be able to take the energy, calculate the frequency from that, and then compare it against the 3 frequency ranges that you've memorized. Does that make sense?